Hello, can you hear me? Yes. All right, so we will begin where we left off last time, which was discussing the supersymmetry spectrum in the context of solving the problems of low-scale supersymmetry. There's lots of great things about low-scale supersymmetry, which we mentioned, and then there's these difficulties of flavor, CP violation, Higgs mass, direct search limits, etc. So how do we go about solving those? And one way to do it, as we alluded to last time, was making the scalar superpartners very heavy. The squarks and the sleptons much, much heavier than the fermionic superpartners, the charginos, the neutralinos, the gluinos. This goes under the names of split supersymmetry or PeV scale supersymmetry. I've worked on this. Arkani Hamed, Dimopoulos, Giudice, Romanino worked on this, and for a few years there was a flurry of activity, and this scenario has been investigated rather thoroughly. And it's a very interesting pedagogical scenario as well for students, because you can see some of the implications of changing superpartner spectrum semi-radically, what that will do to phenomenology and how theory, model building, is affected by it. So this is a somewhat unnatural approach to supersymmetry, and I want to spend a few minutes justifying the approach. So the first thing I should say is that electroweak scale naturalness, where the superpartners are very close to the weak scale, is a murky and controversial subject. So if somebody tells you that 300 GeV is okay for superpartners, but 500 GeV or 1 TeV is not, then of course the next question to ask is, why isn't 1002 GeV okay or not okay? And it becomes very difficult when you try to quantify what you mean by naturalness to state precisely what the criteria are, the demarcation between natural and unnatural. And I think this is a philosophical aspect that we may wish to get rid of. And one of my definitions of philosophy is when reasonable, honest, well-informed people have very different viewpoints. That's philosophy. And I think this is naturalness problem is a somewhat philosophical problem. And so the interesting exercise is to delete it from our vocabulary and ask ourselves, what best supersymmetric model would be consistent with all the data, more solid things that we know than murky issues like appeals to naturalness? Well, your first thought would be, let's just make supersymmetry arbitrarily heavy. Let's make it the gut scale. Why add these new particles? But there are some good things that are data-driven or quasi-data-driven that we may wish to retain. One is gauge coupling unification. Within supersymmetry, gauge coupling unification looks very nice. All three gauge couplings unify well at the high scale compared to the standard model. There is a light Higgs boson mass prediction within minimal supersymmetry. And the data is suggesting that there may be a somewhat light Higgs mass. Actually, for a long time, the data has been suggesting that. In the standard model, the Higgs boson mass could have been anywhere from 0 to a TeV and not have any troubles with it. In supersymmetry, the mass range needed to be between sort of some MZ scale times a trigonometric factor plus some radiative corrections. So it should be right around MZ, somewhere in the neighborhood of MZ. And we're seeing indications that it's somewhere around MZ. Radiative corrections from leptase and tevatron precise measurements of the top and the top quark. Those combined measurements told us that the quantum corrections due to the Higgs mass the Higgs boson needed to be somewhat small, and a 95% confidence upper limit was around 170 GeV from precision electroweak alone before LHC even turned on. So for a while we've known that light Higgs boson mass prediction was an interesting and useful aspect of a supersymmetric theory. And so that's more data-driven. And the third is very data-driven, which is cold-dark matter of the universe. There are indications that, well, very strong indications that there's more to this universe than what we have seen in the laboratory. The galaxy rotation curves seem to show that cold dark matter is required within the halo of the galaxy, and large-scale structure, cosmic microwave background radiation, lots of different pieces of cosmological and astrophysical evidence combine to suggest that we need a fair fraction of cold dark matter in the universe. The omega h square needs to be about 0.1. And supersymmetry gives that to us almost for free. The whole supersymmetric MSSM was understood and established before it was known that there was an excellent dark matter candidate in it. I can tell you the history about that if you want during the tutorial time if you want to ask me about that. So let's make a statement, a comment about gauge coupling unification. I like to define what's called a proximity factor. So if I take the gauge couplings at the low scale, measure them very precisely, alpha 1, alpha 2, alpha 3, and then run them up to the high scale, from the infrared point of view, I can unambiguously state a unification scale, define a unification scale. And that is where the renormalization group flow of alpha 1 and alpha 2 cross. At that point of crossing, there is a scale. We can call that lambda m sub u, the unification scale. The strong coupling constant is not equal to that unified coupling at that scale. And when I first got into particle physics, I remember conferences where people were very upset about even a small difference between G1, G2 unification and G3, but it doesn't, there's no issue. There should be a slight difference because there's high scale threshold corrections. They're expected. Now, how large should those high scale threshold corrections be? They should be a loop factor, probably a loop factor. This unification is with perturbative couplings. So it's some G3 should be G3 at mu plus, the unification should be G3 at mu plus some loop correction with this coefficient A. And that A is proportional to the index, the sum of the indices of the representations that are involved in high-scale threshold corrections, times logarithms of that high-scale threshold correction over mu. So I call that the proximity factor. In the MSSM, this unification scale is about 2 times 10 to the 16 GeV, and is almost independent of the masses, the superpartner masses. It's always right around there, 2 times 10 to the 16 GeV. And this proximity factor is 1. If you can do this at 2-loop level from weak scale up to the high scale, you find this unification, you look at G3, you see the difference, and you measure, so to speak, what this proximity factor is, A. And it's 1. It's about 1, which is right around what you would expect. It's actually, it might even be somewhat smaller than you expect. It's an extraordinarily tantalizing unification of all 3 couplings. In the standard model, if you were to do this exercise, mu would be around 10 to the 14 GeV, which creates a separate set of problems with proton decay, which I won't talk about here right now. But that creates a whole separate set of issues about the low-scale unification. But if I forget about proton decay and I just ask myself, is that a reasonable unification within the standard model? If I apply the same algorithm, and A in this equation would be 20 in the standard model. So, it's a proximity factor of 20 versus 1 in the standard model versus MSSM. And I think I think a case can be made that the MSSM has better gauge coupling unification properties, significantly better gauge coupling unification properties than the standard model. Relic abundance. All right, so here's a small bit of history. Steven Weinberg noted, this is another case of the rich getting richer, right? This guy, I mean, he's done everything, right? And he wrote a paper in 1983, well after supersymmetry was understood as a model of potential model of nature. He said, wow, the LSP is stable. The lightest supersymmetric particle is stable. This could be a problem because this Benjamin Lee and Lee Weinberg paper showed that stable particles could cause a problem, right? Overclosure of the universe, matter domination too early. Is this a problem? And he answered the problem. He answered the question, no, it doesn't appear to be a problem. And then he said, wow, it might even be a good thing. It might be our dark matter. And not too many PRL pages later, Chaim Goldberg wrote an article saying that, well, it's a special kind of particle. It's a Majorana particle, the LSP. So its antiparticle is the same as itself. And it forms an even better dark matter candidate than one might have thought initially. It's better than sort of like a neutrino, a heavy neutrino. So that was a classic paper from 1983. Now, what does this say about the supersymmetry mass scales? And we can do rough dimensional analysis to understand this. The relic abundance is proportional to 1 over the annihilation cross-section. Now, that makes sense, right? Because in the early universe, things are hot. They're interacting. They're annihilating. Supersymmetric particles are annihilating into standard model particles. And as the universe cools, the thermal abundance goes down rapidly. And they're still interacting. And at some point, their interactions are not quite strong enough to keep up with the expanding universe. And then they fall out of thermal equilibrium. They go through a freeze-out. And that time at which they go through a freeze-out is much later if it annihilates much more rapidly. And so it's inversely proportional to the annihilation cross-section. The more it annihilates, the more they go away, these particles. So it's 1 over the annihilation cross-section. If I do just simple dimensional analysis, the annihilation cross-section is some coupling alpha over m tilde squared over SUSY mass squared. So I put that just goes into the numerator now. And I have the relic abundance is proportional to some astrophysical constants, some interaction gauge constants, times mass squared of the superpartner spectrum. That puts a limit on how high m tilde can be, because the relic abundance cannot be much greater than 0.1. The CDM limits, the experiment tells us that it's right around 0.11 plus or minus 0.01. This leads to an upper bound on the lightest supersymmetric particle mass, although others could be much heavier. But certainly the lightest supersymmetric particle mass is bounded. And if you assume electroweak strength type couplings, you find that m tilde needs to be less than a few TeV. Wow, a few TeV, electroweak object, a few TeV, that's a huge challenge for a collider to find. So this kind of analysis does not necessarily state that the LHC is going to find the dark matter or supersymmetry. And remember, I'm deleting naturalness from all of my considerations. I'm just thinking data only. And I have a limit of a few TeV. So supersymmetry, lightest supersymmetric particle could be anywhere from 0 to a few TeV. Okay, so where are we at with this right now? Ignoring naturalness, we have eliminated some bad things. Flavor-changing neutral currents, some proton decay strains, CP violating problems, a too light Higgs boson, because if the supersymmetry were really natural, the Higgs boson radiative corrections would not be so large, and it would be very difficult to get above 114 GeV, much less 125 GeV. But we've preserved good things. We've preserved supersymmetry. Maybe there's many of you in this audience who think that supersymmetry is a wonderful thing to keep in your 4D theory. Light Higgs prediction, gauge coupling unification, and dark matter. And all this can be accomplished by having large scalar SUSY masses but light fermion SUSY masses, gauginos and exenos. So the question to ask is there a good theory for this? And the answer is that there is a good theory. There's a good approach, theoretical approach to it, which I will now go to here. Full screen mode. So the idea is this. In supersymmetry breaking, remember in the CMSSM when I described, I had a slide similar to this that was the second slide, maybe the second slide of our lecture yesterday. And I said that supersymmetry breaking can be analyzed as a spurion in the Kähler potential and the superpotential. So for squark masses, I have x dagger x over m Planck squared, and I do my d4 theta integral. I pull out the f term of this multiplet, this chiral multiplet, and I get out that the squark masses are f dagger f over m Planck squared. On the other hand, if the gauginos are just x, it has to be holomorphic, right? It's a d2 theta integral, so it has to be holomorphic insertions of this spurion. And if x is a singlet, which is the normal assumption and a long time assumption about supersymmetry breaking was, well, why not be a singlet? These old Poloni models, etc. A pure gauge singlet. You add that, you integrate, and you get a gaugino mass like we did last time. However, if it is a non-singlet, if it's charged under any kind of symmetry, then x dagger x doesn't care. It's going to be invariant under that. But x does care. And you can bar it from this interaction. If we assume that the cosmological, well, yeah, as I said last time, if we assume the cosmological constant is equal to 0 to have a cancellation of it, the gravitino mass is also f dagger f over m Planck squared. That will become important in a few moments. So far we have, we're going in the right direction. We have the squarks are gravitino mass and heavy, but the gauginos have no mass at all. So that's a disaster. Experiment has decidedly ruled out gauginos having no mass. But it was shown some time ago, it was actually shown even earlier in some string theory papers, that there's quantum corrections to all of these low-scale mass predictions. And in the case of the squarks, these quantum corrections are not so important because they're 2 loop down compared to the gravitino mass. But for the gauginos, the mass is 0 already. So I need to have some kind of insertion loop correction will be dominant. And that dominant loop correction is proportional to the beta function. You can go through the analysis of this. It's in the old supergravity literature, there's this conformal compensator approach to supersymmetry breaking, and you can insert them judiciously in Lagrangian and find that you get out, in fact, this kind of, if you go through all the steps, you get out this one loop mass. Now, being proportional to the beta function gives us a very different spectrum for gauginos than what the minimal supergravity showed us before. If we recall, our spectrum before was the lightest gaugino was the Bino, the superpartner to the hypercharged gauge boson. And that was 40% of the gravitino mass. 80% of the gravitino mass was the Wino, and then 2.5 times or so higher than the gravitino mass was the Gluino. But now we have this quantum correction as the dominant source of supersymmetry breaking transmission to the gauginos. And the lightest gaugino in this case is the Wino, the superpartner to the W. And the second lightest is the Naturalness M1, the Bino, M1. And the heaviest, still heaviest, is the Gluino. And these are a loop factor down compared to the gravitino mass. So even the Gluino is a factor of 40 less than the gravitino mass, modulo some additional quantum corrections. But the scalar masses are very heavy. The scalar masses are at least 40 times heavier. So this spectrum is a very interesting one. And let's race right to Higgs mass prediction in this scenario. Okay, I find this interesting because split supersymmetry, so let's call it split supersymmetry, predicts a significantly higher mass for superpartner, for the Higgs boson mass, than let's call natural supersymmetry, CMSSM. And what I am showing is a plot from Giudice-Strumia from a few months ago of contours of lightest Higgs mass and supersymmetry in the plane of tangent beta. This is the ratio of the vacuum expectation value of the two Higgses, and the supersymmetry breaking scale, GeV. Now, the supersymmetry breaking scale, you should think of that as the scalar gravitino mass, the scalar superpartner masses. Not the gaugino masses, the scalar superpartner masses. And you see that what I had proposed earlier was that the scale should be around a PeV, 10 to the 6 GeV. Okay, if you have 10 to the 6 GeV for your supersymmetry breaking scale, one can easily accommodate 125 GeV contour. This green contour is 125 GeV. If tangent beta is about 2. And 2 is a nice round number, order 1. So this is a nice connection between 125 GeV Higgs and the PeV scale superpartner spectrum for low values of tangent beta. But under much of the higher values of tangent beta, it's a significantly lower scale. And so if you go to higher gravitino mass scales, you would get something like 130, 135, even 140. In the original sort of split supersymmetry literature from a few years ago, the anticipation was that the Higgs mass would be greater than about 130. So what you're seeing here is a pressure, the Higgs mass signal, if it indeed is there at 125 GeV, is pressuring two different approaches of supersymmetry from two different directions. So the radical naturalists, as I talked about last time, would say 125 is uncomfortably large mass for the Higgs because I want low-scale superpartners and I want the electroweak potential to be natural. And I turn the crank, and it's really difficult to get 125 GeV Higgs mass out of that. That's too high. For others who like this sort of data-driven approach and just completely ignoring naturalness, it's pressuring it from the low end. 125 is just a bit too small, a bit too low from this perspective. Maybe it's not too low if you are okay with tangent beta at that point. But it's a really interesting value for the Higgs boson mass. It's extremely interesting from the theoretical point of view. I can't overestimate how interesting, or overstate how interesting 125 is. It's really interesting from the theoretical point of view and the phenomenological and experimental point of view. From the theoretical point of view, In supersymmetry, it pressures both scenarios from bottom and top. From the standard model point of view, it's on the threshold of sort of vacuum stability issues and, you know, where are you at with respect to, is the universe going to last forever, or forever in quotes, or is there some problem, new physics has to show up before the Planck scale? From the phenomenological point of view, the Higgs boson can decay, has many different non-trivial branching fractions into photon-photon, to ZZ, to WW, to B's, to everything. So I just wanted to spend 30 seconds telling you how exciting 125 GeV Higgs is. Okay.
What made you prefer value 10 to the 6 in this diagram?
So in the next slide or two, I think it is, I will show you why 10 to the 6, I believe, is sort of the ideal scale, PeV scale. I think it's here. So it's from the dark matter point of view, so it's a good question. So before I sort of stated it roughly that 10 to the 6 was what the PeV scale was best, but now I'm going to show you why I think it's a preferred choice from the split SUSY point of view. And it's because the lightest supersymmetry particle is the Wino. And the Wino annihilates very, very effectively. It's part of a doublet, a triplet. So W0, W plus, W minus. It's got charge. It interacts with SU2 quantum numbers. In contrast to the Bino, which is the standard LSP and dark matter candidate, which really doesn't like to annihilate at all. It has a tough time annihilating. And it's got hypercharged quantum numbers. It's a Majorana. It doesn't couple to anything on its own. You have to go through T-channel sleptons or have it mixed with Higgsinos. But Wino, the Wino multiplet all on its own annihilates very effectively. Yes? It's a part of the, it's the SU2 part of the Z. Yeah. Mm-hmm. So on the Wino mass, if I scale up the Wino mass, then the Relic abundance, the prediction, I can do a Boltzmann equation. I can follow the Boltzmann equation in the early universe and make a prediction for the Relic abundance. As I scale up the Wino mass, there's just no particles left. The Relic abundance is zero for very small for low Wino masses. But as I go higher and higher, I finally reach this range of about 0.1 for the Relic abundance. And that range is at just above 2 TeV. I think this is a slightly higher number than I should have written. But just above about 2.5 TeV is what the Wino mass needs to be. So this pure data-driven approach is telling us that the lightest supersymmetric particle is 2.5 TeV. The 2.5 TeV Gluino would be difficult for LHC to find, much less an electroweak object. So I'll talk about the challenges of that in just a moment. But this is the scale that we're getting at. Now, what does this mean for the rest of the spectrum? If I have the Wino mass of 2 TeV, and that's how I'm anchoring the full supersymmetric particle spectrum, is through this data-driven value of a thermal relic, a nice thermal relic. This is the anchor number. Then I get the Bino is 6 TeV, the Gluino is about 14 TeV, and the scalar masses are about a PeV. If it all goes this way, there's very little hope for supersymmetry direct detection at the LHC. A lot of hope for the Higgs, of course. The Higgs will be found, but the super partners would not. And so if you look carefully at all the different phenomenon that could have access to this kind of spectrum, probably the most appealing or most viable thing is to look for Wino annihilations in the galactic halo into monochromatic photons. So you have several TeV Winos, they annihilate through a loop into photons. It turns out that the highest cross-section that you can get in supersymmetry for neutralino annihilations into photons, monochromatic photons like this, is through Winos. Not through Higgsinos, not through mixtures, not through anything, but pure Winos. So this is so in astrophysical types of observations of monochromatic photons would be the best. So far they haven't seen them, but they're not particularly sensitive to them yet.
In this scenario, the LHC will see the Higgs this year?
Yes.
And then nothing else since Rock.
Right. In this particular scenario. But there's a way out that I will tell you about right now that is very intriguing. And it has to do with another problem of supersymmetry that I've glossed over before. And you could even call it a data-driven problem. And that is the gravitino mass and the gravitino. So the superpartner of the graviton is a nasty object. It really creates problems. If its mass is between a keV and a few hundred GeV, or certainly probably even a few TeV, then if you're not careful and don't do things cosmologically, don't do special things, then after inflation, you can produce these gravitinos. And then when do they decay? They decay at a very inopportune time during Big Bang nucleosynthesis generically. And this is the so-called gravitino problem of supersymmetry. And there's ways out. There's always ways out. You can make some cosmological model that makes sure there's not many gravitinos around at that time. You can fool with inflation. You can do other things. But generically, if you have a fair number of gravitinos roaming around after inflation, they will decay during Big Bang nucleosynthesis and disrupt the relative number of these elements, these light elements. So, but if the gravitino mass is higher, heavier, and heavier, then there's not a problem. Because the heavier the gravitino mass, the quicker they decay. The partial width is proportional to the mass. Well, actually, it's proportional to a higher power to the mass, depending on how you phrase it. And it decays before Big Bang nucleosynthesis. And so no problems with Big Bang nucleosynthesis. If I have a gravitino mass of a PeV or several hundred TeV, no trouble with Big Bang nucleosynthesis. But there's an opportunity also. So there's no problem plus an opportunity. The opportunity is that it will like to decay still rather late and after freeze out of the lightest supersymmetric particle. So the lightest supersymmetric particle is interacting, and then it freezes out. And then after it freezes out, there's no more real annihilation to speak of, and its relic abundance is sort of set. And the universe cools down. You have to take that into account, but it's set for life. So, but imagine that the Wino, the LSP, is annihilating, and it freezes out, and there's lots of Winos floating around, and then suddenly the gravitinos decay. And this is what can happen in this scenario. And the gravitinos, when they decay, they'll cascade through lots of different things. They'll cascade through quarks and whatever. But in the end, they have to go to the lightest supersymmetric particle and stop. The LSP is not going to decay further. And that is the Wino. So the gravitino will decay into that, will decay into the Wino, and you have an extra source of dark matter, a so-called non-thermal source of dark matter. And it is extremely effective. And some people would go so far as to say that it's generic to get a large contribution from this source to dark matter. So the proper thing to say, given this, given constraints from thermal history and this non-thermal approaches, is that the Wino mass can be anywhere from 0 to 2.7 TeV. And still be a good dark matter candidate. Okay? It just merely needs to be less than about 2.5 TeV. Okay, so now let's ask, we can scale the whole spectrum down. We are no longer anchored at 2.5 TeV for the Wino. We have a non-thermal source to generate our dark matter. So we can anchor our spectrum at any scale we wish. So let's go down to the lowest scale possible. Well, actually, yeah, this is about the lowest scale possible. It's 100 GeV. And by the way, this spectrum is right on the edge of being ruled out of LHC. Probably is not ruled out by LHC quite yet. Hard to know. But it's right on the edge. And the gravitino mass and the scalar masses are above 30 TeV. So they're irrelevant. They're way up here, totally irrelevant to any LHC phenomenology. So the lightest are the Winos, and it comes in a triplet. Wino 0, Wino plus, Wino minus. The next is the Bino, and the Gluinos are here. And then everything else is out of reach. Scalars out of reach. Binos are just not produced. If you want to think about it as an exercise, think about why the Binos are not produced. You can estimate what the production cross-section is. Really, really low. You have to go through squarks. Higgs mass predictions needs to be below 140, and Wino and Gluino production can give colliders hope. But the Wino, so I'm going to spend a couple of slides showing you why, even though the Wino is 100 GeV and it's produced in a triplet and it's produced copiously, you're not going to see it at the LHC. And there's interesting phenomenology in this. This is particles. This is real fun particle physics involved in here. And it's the mass splitting of the charged and neutral Wino occurs by an operator like this. You need non-trivial gauge indices between the Winos in order to get a mass splitting. So you need to somehow separate out the triplet components. So this mass, this MA coefficient, has to transform non-trivially under SU2. How can we get a mass interaction that transforms non-trivially under SU2? There's only one way, and that is by the VEVs of Higgs fields, making an operator of Higgs fields, putting in SU2 generators, and then the vacuum expectation value of the Higgs throws SU2 charge into the vacuum, which makes this charge transform non-trivially under SU2. This is the leading operator that can do that for the Wino. It requires 4 Higgs insertions to do it. So it's a rather high level operator. This is the scale of sort of the mu term and the Bino mass and so on. And it turns out that if I look at the mass splitting between the charged Wino and the neutral Wino, and I plug in supersymmetry spectrum and so on, I find exactly this. I can do the calculation directly, and that operator approach from the previous slide is an appropriate one. I have 4 Higgs insertions. The MW to the 4th power is 4 VEVs, divided by a lambda cubed, which is M1 minus M2 times mu squared in this particular case. And I have another term that's similar. This decouples extremely rapidly. M1 is a rather high mass value, and mu typically is a rather high mass value in this scenario. So the tree level, this is a so-called tree level mass splitting of the Winos, the lightest chargino and the lightest neutralino. And by just doing those matrices of the second and third slide of yesterday's lecture, you can do this. You can compute this yourself. And you can also show and convince yourself that this decouples to 0 very, very rapidly. So the mass splitting is not more than a few MeV from tree level contributions. But there's a one-loop contribution, which is a very curious one. It's not a UV effect. It's an IR effect. So if I have, so try to think spatially here. So this is true particle physics. This is like pions. So if you're familiar with pions, this is just like that, except for, yeah. So think spatially. as I go to really short distances, there's not a difference between the W0 and the W0. It's the SU2 is reestablished. There's this SU2 cross U1 theory and so on. But as I go away from really short distances, then I have SU2 breaking in the IR. And from a long distance away, it's obvious that there's a huge difference between the Wino 0 and the Wino plus. One's charged and one's not. There's this long-range photon interaction. So basically, you can do this one-loop calculation without thinking. You can just write down and just calculate. Look in the back of your book and write down Feynman diagrams and calculate. But basically, it's an integral over an energy density in the IR, the difference from something charged versus non-charged. And you get out this result, which was an extraordinary disappointment. It was 165 GeV. Anybody know why that would be really disappointing? 160. What's that? Yeah, MEV. Sorry. Yeah. So it's a one-loop effect. So I have sort of 100 GeV-ish Wino multiplet, and the mass splitting is 165 GeV. It was very disappointing that it was 165 GeV. MEV. I'll give you a hint. I wish it were less. What would happen if it were less? Why would I be able to see it?
Well, it pushes the mass down. If it's GeV like you want.
No, I want the mass splitting to be less than 165 MeV. Yeah, I would have preferred that. And when I go from 165 MeV and I make the mass splitting less and less and less, what happens? Oh, okay. There's a threshold is not allowed anymore. And so this number 165 is close to the pion mass, but it's above the pion mass. So what happens is that this poor object, this charged Wino, from one loop of X, has a mass splitting of at least 165 GeV plus the tree level part, so 165 MeV, and it decays a two-body charged Wino into neutral Wino and pion. And this is a disaster because it's prompt. This is you can work this out through. It's really fun. You read these wonderful old papers. Your generation, you're amazing students, right? But this generation before us was they were this PCAC, charged pion interactions. All that literature is really, really fascinating. And it was known a long, long time ago of sort of baryons and other things that how to compute these kinds of decays. And you say, well, this isn't really a two-body decay, but yeah, under partially conserved axial current computations, this is a two-body decay. I know that pions are made of quarks, and you know that too, but these are extremely soft, low energy, less than lambda QCD, and the phase space truly is it asymptotes to a two-body phase space on shell decay of a neutral Wino and a charged pion. Boom, right there, and it's prompt. So visions and hopes of a charged Wino being produced and then plowing through the detector as some renegade charged object, and then having everything light up and seeing it, are dashed by this one-loop computation because there's a very prompt decay into the dark matter, so you're not going to see that, and a pion. So you can do some interesting kinematic calculations to ask how energetic will this pion be. It's not going to have any energy, hardly. And nothing in this diagram past the triggers of the LHC experiment. And what will happen is that these will escape all detection, the pions will be produced, and they'll just curl up and die immediately. Nothing is seen. The only hope to see to see Wino production at the LHC is to take a gluon, attach it to this initial state, and radiate it hard. And so a gluon radiated from here at, say, 100 GeV, that triggers the detector. You see 100 GeV gluon plus some missing energy. And then maybe you can, I doubt you'd be able to do this, but maybe you could look in the inner workings of this and see these pions curling up. But there's so much mess in these detectors that it's unlikely that you could do that. But you could see evidence of non-standard model rates of gluon plus missing energy. But it's extremely difficult because there's lots of other sources of gluon plus missing energy, right? You can make gluon plus neutrinos, purely standard model thing. So a gluon and a Z boson where the Z decays into neutrinos, a huge rate there. You have to compete with, this has to compete with that. So this is challenging to say the least. So this was one of our two best hopes to find supersymmetry in this scenario, and it looks like it's being dashed. LEP at E plus E minus colliders, it's a much cleaner environment, and it's easier to do it. The limits, this is the mass difference between the charged state and the neutral state. So for us, it's 165 GeV. And this is a purely phenomenological analysis, so they just assume the mass difference could be anywhere between 0.1 and 5 GeV. So this is the Aleph collaboration from about a decade ago. And the limit is about 90 GeV. That's what's applicable for the Wino. And above that, no hope until an E plus E minus collider is built, probably. Another E plus E minus collider. All right, so that's dashed hope 1. What about hope 2? The gluinos. Much more hope with the gluino. The gluino is a strongly interacting particle. It can be produced all on its own. Gluino production through gluons, through quarks, etc. The rate is very high at a 14. This is the rate at a 14 TeV LHC. The main decay of this particle is 3-body. You can make 2-body decays through gluino and gluon and lightest neutralino, but under most of the parameter space, the 3-body decay dominates. And it's a gluino decaying into a quark and an off-shell squark, a very off-shell squark. That squark is 40 TeV at least. And then that off-shell squark decays into a quark and a Bino, Wino, or Reno. And most frequently into Wino because it's a more strongly interacting particle. But now, the preference is the third generation particles. So the lighter the squark, the higher the branching ratio to its corresponding quark. So this is an off-shell. This propagator has an overall smaller value if the squark mass is very heavy. So the preference for this decay mode would be to whatever intermediate squark is the lightest. So now you have to ask yourself, what is the lightest squark in this spectrum? And there's no telling. One of the beauties of this scenario is that we haven't really cared about flavor. If you're doing natural low-scale supersymmetry, you're spending a lot of time making sure that the flavor angles line up here and line up there, and you have a real story to tell about the hierarchy of various flavor superpartner masses. In this approach, the scalar masses are heavy, and they're not really causing too much problem in flavor, and it doesn't really matter so much what the relative hierarchies of the flavors are. But there's a generic tendency for the top squark to be lighter than the other squarks. So certainly if they are all unified at the high scale, as we showed last time, the squarks that do not have any Yukawa couplings associated with them run upwards and rather steeply upwards, due to Gluino radiative correction logarithms. Whereas if you have a squark that feels a rather large Yukawa coupling, like the top squark does, it pushes it downward. And so in the low-scale spectrum, the top squark is expected to be lighter than the other squarks. And so this is the generic preference for decays into third-generation quarks. Okay, so high multiplicity tops and missing energy events. The simplest event type is the upper right-hand diagram. You produce gluinos, and the gluinos decay into 4 tops and missing energy. There are possible lower rate combinatorial cross-sections of 6 top quarks and 2 bottoms and 2 pions plus missing energy. You can get high multiplicity top quarks and high multiplicity bottom quarks. That's the generic prediction of this kind of scenario at the LHC. And it might be the only way that supersymmetry directly manifests itself at the LHC in this scenario is through high multiplicity top quark events and missing energy. So the comments on this intermediate phase of my lectures is that if we think of inputs as SUSY partners are heavier than LHC7, so we obviously have not seen supersymmetry yet, so that's an input to how we should think about the world. The second input of how we should think about the world is that there are direct Higgs limits of 114 GeV to 140 GeV approximately, and maybe even a Higgs signal at 125 GeV. And then, of course, the other inputs that I talked about, gauge coupling unification, dark matter being viable, the gravitino problem being solved, etc. The outputs are that perhaps there's a high non-minimality for natural SUSY, or we can just delete naturalness as a criteria, and then I believe we are led to a split supersymmetry approach if we delete that philosophical notion. And in case 2 here, the LHC discovery hope likely rests in multi-top quark production. Okay, so now I'm going to let you take a 5-minute break, but I am going to go directly to unification studies. And let me just preface in 60 seconds what I'm going to do in the next lecture. I'm going to show you, I'm going to try to show you the sensitivity, what's sensitive and what's not to high-scale assumptions for low-scale supersymmetry. And I'm going to resuscitate minimal SU5 at the end, if I have time. And at the beginning, I'm going to do a so-called revisiting of B-tau top unification within supersymmetry and show you that assuming a grand unified unification of third-generation Yukawa couplings has a real profound effect on the low-energy spectrum. Okay, so we will break till when?
Yeah, till 12, but maybe you want to take a couple of questions before we do so.
Okay. Yes. Questions, please.
Okay, so there'll be more questions after the break, hopefully.
All right.